Today we're going to look at another aspect of what integration can do for us here and talk about the lengths of curves. So we suppose we have a curve, so some function like this, and an important fact that we need to proceed here is that our curve has to have a continuous first derivative on our interval, and it's got to be from our a to b. All right, so we see a to b there. And so determining the length of the curve is similar to determining how far you would travel if you walked along the curve from one point to the next. So we'll call that arc length, and we'll use the letter capital L for that. So it says we're going to use the distance formula and the mean value theorem to determine a formula for arc length. So distance formula, right, that's going to be using some sort of right triangle. So what we're going to do is you can see that we have kind of our interval broken up in a kind of a partition. We've only got sort of our 3 points that we're working with now. And as you probably remember from all of our Riemann sums, we would eventually have more and more of these partitioning points and then take a limit. So we'll go ahead and take a look at some right triangles that deal with this partition. So I'll first mark off the points that are on the curve at each of these partitioning points. And we're going to be approximating the length. And so we'll go ahead and get an idea of what we're approximating here, just the distance from one point to another. Right? If we want to find the distance from this point to this one up here, we'd use the distance formula. And the distance formula uses this right triangle here. And so to find to the next point, we would use this triangle here. Right? So we have x sub 0, y sub 0 for this first point, x sub 1, y sub 1, x sub 2, y sub 2. And so we'll use this pattern for our naming scheme. Excuse me. Eventually, we'll start saying, well, let's call the last one x sub n, y sub n. And we'll call any of the ones at the beginning or middle or end, basically the indexing version. We'll go ahead and say, well, what if we replace the zeros? We could just say this is I. So I'll call this x sub I, y sub I. And then this will be I plus 1, I plus 1. And we'll go all the way to where I is equal to I is equal to n plus 1 here. Right. Oh, actually, we're going to start at 1 and go to I equals n. Sorry. So just looking at what is the distance from one point to the next, we're looking at something like then distance formula says we're looking at the distance between. So I'll go ahead and mark what I was talking about before there. I'll actually go ahead and call this x sub I, y sub I. We'll call the one before it I minus 1. So we'll go ahead and look at the distance between the x's here. Right, distance formula, we find the difference between those guys and we square it. Plus, and then the distance between the y's. All right, so that's going to be the distance along one hypotenuse. We want the distance along all the hypotenuses, so we're going to have to do a summation depending on how many partitioning points we have. All right, we're going to start out with I equals 1. Right, that'll give us the first one. Will be the 0th. Right, the second one will be the first, and so on, all the way up to n. Right, and so what we're going to do then is we're going to say, what if we have then an infinite number of these partitions? Right, and this is how we make that jump then. We'll make that jump from our summation to our integral. And this will give us then our arc length. All right. So that's our starting point. It's going to get kind of tedious to write these down every time. One thing that we do know is, let's see, we can well, the typical thing is to use a delta to denote the distance between two objects here. So we'll do that. We have delta x is the distance between two of the x's. And then we'll have delta y sub I would be the distance between the y's. So one thing that we know is that we don't have to use delta x sub I. It's not going to be different for each triangle. Because we have a regular partition, these horizontal bits of our triangles will always be equal to each other. So instead of delta x sub I, we'll just use delta x. So the reason is the delta x sub I are all the same length. Since it's a regular partition. But the delta y sub i's could be different lengths. We see that we have two triangles with very different lengths. So we're going to have to keep that as delta y sub I. That will be dependent on I. So I'll go ahead and make that replacement here. And so we'll have delta x squared plus delta y sub I squared. All right. And so what we could theoretically do then is we can actually start moving this guy around. We kind of want to say maybe if we can take this guy out, factor it, something like that, we could get something cool going on here. Since we have that kind of stark contrast now between these two deltas. So what we'll do is, let's go ahead and factor out delta x quantity squared. Another thing that we can see is we have a delta y and a delta x that vaguely looks like our slope formula. And it'd be nice if we ended up with a delta y over delta x. Right, so we'll go ahead and factor out this delta x squared. Right, and so we divide by what we factored out. And that's pretty much what we get then. All right. So we've got the limit as n tends to infinity. We've still got this summation here. Right, and we can split the square root over multiplication. So we can actually split this into two different square roots. And this is 1 here. And we've got delta y sub I over delta x. And now this whole thing is being squared instead. And the square and square root cancel over here. All right. So next, we want to figure out, we can tell, again, that this should be some sort of, maybe a slope or something like that. Right, so this is where the mean value theorem comes in. So the mean value theorem says, if we are continuous on a closed interval, which we had to be as part of our prerequisites here, if we are continuous on a closed interval, and we are differentiable, right? So we have that continuous first derivative. Then there has to be some point, remember, where f of b minus f of a over b minus a is equal to f prime of c. So we have our f of b minus f of a here, and we have a b minus a. So we know that there's got to be a point sort of in that region where we are equal to some derivative value. Right, and so what will happen is, as n goes to infinity and these guys shrink down, we'll end up just with that single derivative value kind of left. Right, so that's how we get to our derivative. Somewhere in each of these guys here. All right, so we'll go ahead and make that swap. And we don't really want to introduce c here because, well, if we're looking toward making an integral, then we're going to want to mostly use x's. So what we'll do is we'll denote that with, so we swap this out for f prime of something. All right, it's going to be something that comes out of, it's going to come out of this particular delta x here. Right, it's got to be a specific point though. So we'll call that an x sub I again, but we'll say it's a special one that makes the mean value theorem true. We'll put a star on it. All right. So then we'll go ahead and take our delta x, we'll kind of shove it at the end, and we'll explain how we get to the integral part. So f prime of x sub I star quantity squared delta x. Right, and so now we have the width of our rectangle and the height of our rectangle. And so these are the necessary steps we need. We'll go ahead and turn this into the integral from a to b of root 1 plus f prime of x quantity squared, and that delta x turns into a dx. And so this is going to be our arc length formula. Now we're not going to have to derive this every time. We'll just go ahead and talk about the definition here. If we have a continuous first derivative, we are going to have to show that happens. The length of the curve is going to be given by this formula, and we are missing the prime. That's important. I'm going to expect you to actually find the continuity. So what we're going to have to do for each of these problems is we are going to have to take the first derivative and show that the first derivative is continuous on these values. That is important. I do expect you to do that. It's not necessarily a lot of work, but it is something that, we need to check just to make sure that we're doing the right thing here. So we'll go ahead and find the arc length of this curve. The first thing we're going to need to do is find the derivative, the first derivative. Right, it's a power rule, so 3/2 x, and we subtract 1 from 3/2, and so that's our first derivative. It's going to be 3/2 root x. Right, and we'll go ahead and talk about the continuity. Right, this guy is going to be continuous, and I'll put continuous as CONT on 0 to infinity, which includes 0 to 4. And so we can go ahead and proceed. So we'll integrate from 0 to 4, root 1 plus this derivative squared, dx. So we've got the integral from 0 to 4, 1 plus 9 over 4x dx. And we'll use a little u substitution here. So we'll let u equal 1 plus 9 over 4x. So du will be 9 over 4 dx. We don't have an extra 9/4 kind of floating around there. We'll go ahead and bring that to the other side. So 4/9 du equals dx. So now when we swap out our dx, we'll be able to have that 4/9 in there. So 0 to 4, root u, and then we have that 4/9, and I'll go ahead and just put that out front here, since it is a constant. Should be a du. And again, I'm going to go ahead and leave those limits of integration the way that they are. You can go ahead and change them if you want. I'm not going to hold that against you, but this is the way that I prefer to do it myself. So we'll go ahead and integrate this guy. We've got u to the 1/2. So it will just be a power rule. So we have increase the power by 1. And that didn't go right. There we go. Increase the power by 1. Divide by the new power. Dividing by 3/2 is the same as multiplying by 2/3. All right, and we'll go ahead and put x back in. And it was 1 plus 9 over 4x to the 3/2 from 0 to 4. And while we're at it, we may as well multiply these guys together, or bring the 2/3 out, multiply them together, right? So we've got 8 over 27. And then we've got, I'll go ahead and write it one more time this way. So we've got 8 over 27, and I'll go ahead and open some brackets. Parentheses, plug in the 4. My 3/2 fell off. Careful. Minus 1 plus 9 over 4 times 0. All right, so we've got 8 over 27. 4's cancel. We got 10 to the 3/2 minus 1 to the 3/2, which is just going to be 1. So we've got 8 over 27, 10 to the 3/2 minus 1. And we can rewrite this so it looks a little cleaner, I guess. 8 over 27, we got root 10 to the 3rd minus 1. We could even go a little further and write that as root 1000 minus 1. And this would be a length, so we are just talking about units here. And that's going to be our answer. All right, so that's how an arc length problem will look at the most basic level. All right, we've got a few tricks that we can kind of throw in there. So on this guy, we have a couple of transcendentals here. We've got e to the x involved. So again, first step, find the derivative. And it's relatively simple, right? The only thing that we have here is a chain rule, so we bring out the negative as well. Right? And e to the x is nice and continuous, right? So we'll go ahead and write this out as minus 1 over 8 e to the x, so that we can kind of study what's happening here in that denominator. E to the x by itself, continuous everywhere, right? So we just want to make sure that this denominator is not equal to 0. Well, when do we have e to the x equal to 0? That doesn't really happen, but just for further examination, this would happen if we swap this to a logarithm. If x was equal to the natural log of 0, which is negative infinity, that's not a value we can use. So this guy is continuous everywhere. So it's continuous on negative infinity to infinity. So we can proceed to finding the arc length. We'll go from 0 to natural log of 2. And I use a cursive L for my natural logs, just so that it doesn't look like an absolute value bar or a 1 or something like that. I advise you to just make it look different. Right, so we'll have root 1 plus, and we're going to have our entire first derivative here squared. And in this kind of case, what I would consider helpful is to take what's in these parentheses here, set it off to the side, and go ahead and evaluate this kind of by itself. Right, so we'll go ahead and write this out. This is squaring the entire thing here. Because we certainly can't go ahead and integrate this. U substitution won't work either. We don't have enough e to the x's kind of outside the square root. So we'll go ahead and evaluate and hope something good happens. And we'll do that off to the side. We've got first e to the x squared. But we could also turn that into e to the 2x then. Outsides, we've got minus 1/4. And then e to the x times e to the negative x, that gives us e to the 0. Insides, we get the same exact thing. And then lasts, we got plus 1/64 e to the negative 2x. All right. Those e to the 0s turn into 1s. So we got minus 1/4 minus 1/4 plus 1/64 e to the negative 2x. When we add those up in the middle there, those 1/4, they turn into minus 1/2. And so there's not really anywhere else we can go from here. So we'll go ahead and plug that back in. So we got 1 plus, and we could already see we could drop those parentheses. 4 e to the 2x minus 1/2 plus 1/64 e to the negative 2x. So we do have some like terms. We have the 1 and the minus 1/2. When we add those together, we get plus 1/2. And so I want us to pay attention to what happened. We had this guy, right, which had the minus 1/2. The only thing that's different between these two is we have a plus in the middle. Right? This guy over here was factored in this way. If we wanted to factor this, we would get back this. So we have the idea then of what this will factor into. Right? Another way of kind of looking at this is, remember the difference between, we've got a plus b quantity squared, that's a squared, plus 2ab plus b squared. If we had a minus b squared, we would have a squared minus 2ab plus b squared. That's the exact situation we're in here. We had this guy, right, which ended us with a minus 1/2 in the middle. And now we have this guy, which is the same thing, just with a plus in the middle. So we can factor it into a plus. So that's what we'll do. And this is a common trick when it comes to these arc length problems, right? It's going to be very tricky to find good sort of functions that we can take a derivative, square it, stick it under a square root with an addition, and make it still integrable for us. So I'm going to have to rely on this kind of trick to make that happen, unless it's just a simpler function like that square root we found before. So we'll go ahead and factor in. It should end up as this guy with a plus in the middle. So 2 e to the x plus 1/8 e to the negative x quantity squared. And so now the square and the square root will cancel. And we'll end up with just this binomial. And this is going to be relatively easy to integrate. So we'll go ahead and do that. 2 e to the x. And we have to integrate keeping the chain rule in mind here. And we'll evaluate this guy from 0 to natural log of 2. All right, so open up brackets here. 2e to the natural log of 2 minus 1/8 e to the negative natural log of 2 minus 2 e to the 0 minus 1/8 e to the negative 0, which is still just 0. Remember that e to the natural log of x is just x. So here we should have 2 times 2. On the other hand, if we have a negative on the outside of our natural log, remember any coefficient of a logarithm becomes the power. And so this is natural log of 1/2. So we get 1/8 times 1/2 minus 2 minus 1/8. So we get 4 minus 1/16 minus 2 minus 1/8. So we got 64/16 minus 1/16 minus, let's see, we got 16/8 minus 1/8. So 63/16 minus 15/8. That's 63/16 minus 30/16, which gives us 33/16 units. And so that's going to be our result there. All right, again, this is a trick that is going to come up. You can pretty much say whenever we do an arc length problem. So that ending up with a negative 1/2 in the middle, so that the 1 plus that will turn into a positive and you can factor it back out. So be aware of that situation. It's going to pop up. So we'll turn our attention now to what happens if we have things in terms of y. And it's essentially the same thing. We just changed the names of the letters. Also, this should have a prime on it. So again, it works in y as well. We take our derivative, we square it, and we integrate. All right, so we'll go ahead and take a look here. Find the length of the curve x equals 2y minus 4 on this interval. All right, so again, we have our x. We need to find x prime, or dx over dy. We'll go ahead and use Leibniz notation. And it's just 2. And I do want to make the point that this is y. Negative infinity less than y less than infinity. So this is continuity based on y. So I'll go ahead and find the arc length then. We're going from negative 3 to 4. Square root 1 plus, this derivative is 2 squared dy. So negative 3 to 4, we've got 1 plus 4 dy. So we've got root 5. Negative 3 to 4, root 5 dy. And we'll go ahead and evaluate now. Root 5y evaluated from negative 3 to 4. So root 5, 4 minus negative 3. Root 5 times 7, which is going to give us 7 root 5 units. All right, so we'll move on to something more interesting then. So again, we have some transcendentals. And so we can expect that we'll probably have a similar type of trick as last time, but we'll go ahead and investigate as well. So again, we are using y. So we're going to need to figure out this derivative. All right, so let's go ahead and take a look at what this should be equal to. 1/2 e to the y plus e to the negative y. All right, that's one way of looking at it. Or we could look at it as 1/2 e to the y plus 1/2 e to the negative y, whichever you're more comfortable with using. All right, so I'll go ahead and leave it like that. E to the y minus e to the negative y. All right, so that's our derivative. And again, it's going to be continuous. on the entire real number line. All right, so we'll go ahead and move on to our integral here. Excuse me. So we're going from 0 to natural log of root 2 plus 1. Definitely an interesting upper limit there. So we'll take the square root, 1 plus, and we take our derivative squared. And so we're going to have to, again, kind of shove this off to the side for a second and get a clearer picture of what should be happening here. So we're going to go ahead and evaluate off on the side this whole thing. So we got 1/4 e to the y minus e to the negative y squared. Right, we apply the square to the 1/2 as well. That's 1/4 e to the 2y. Multiply these both together. Again, we get 1 minus 1 plus e to the negative 2y. All right, that's first, outside, inside, last. So we've got 1/4 e to the 2y minus 2 plus e to the negative 2y. And remember, we're going to likely be using that trick here, so we're probably going to be most helped if we distribute that 1/4 back out. So 1/4 times negative 1/2 is, times negative 2 is going to give us that negative 1/2, and that's what we're looking for. All right, and so we see that we do get that same pattern going on. So we go ahead and plug that back in. 1 plus 1/4 e to the 2y minus 1/2 plus 1/4 e to the negative 2y dy. The 1 and the 1/2 turn into positive 1/2 here. So 1/4 e to the 2y plus 1/2 plus 1/4 e to the negative 2y dy. And we factor, right? We use that same idea that we did before. Instead of having the negative inside, we'll have a positive. So this will be, excuse me, 1/2 e to the y plus e to the negative y quantity squared. If this is kind of uncomfortable for you to have that 1/2 hanging out, again, you could distribute it and kind of just use this guy from the beginning. And that'll keep things a little bit more straightforward. All right, so that root will cancel. And so we'll have 1/2 e to the y plus e to the negative y dy. We'll bring the 1/2 out front. And so we'll have to evaluate this guy as well. I'll go ahead and bring this up here. And we'll have then e to the y minus e to the negative y evaluated from 0 to the natural log of root 2 plus 1. So we'll open up some brackets. E to the natural log of root 2 plus 1 minus e to the negative natural log of root 2 plus 1 minus e to the 0 minus e to the negative 0. All right, so this is the same quantity twice, so these guys cancel. So we're looking at 1/2 root 2 plus 1 minus 1 over root 2 plus 1, right? That negative on the outside of the log, we use that to basically make this guy a denominator, right? It's a negative first power. So we're going to have to figure out common denominator here, add these together. So go ahead and take this whole thing and multiply it by root 2 plus 1. And that would give us the denominator we want. And make sure your root doesn't kind of grow too large here. It should just contain the 2. So we've got 1/2, let's see, root 2 times root 2 is 2. Outsides, we've got root 2. Insides, we got root 2 again, so that's 2 root 2. I'll just go ahead and include that. And then lasts. Now we've got the -1 from this fraction. These ones cancel. So we've got 1/2 times 2 plus 2 root 2 over root 2 plus 1. We can factor a 2 out of the top there. And I'll switch the order of the bottom too. So the 2's cancel, the 1 plus root 2's cancel, and all we are left with is 1 unit. I really like those answers. All right, so that's arc length. The use is relatively simple, I would say, as far as there's not a whole lot of crazy things I can throw at you, just because we do have taking the derivative, squaring it, then adding 1 and square rooting it inside our integrand. There's not a whole lot of things that we can deal with as far as those kinds of integrals. So we're going to really hang on this kind of trick, that whole -1/2 plus 1/2 thing, or maybe just using simpler functions. All right, so that's it for 6.5. See you next time.